So section 6.5 is approximate integration, and there's several reasons why we would possibly want to integrate a definite integral by approximation. And one of the primary ones is that we might have an integral like e to the x squared dx, and perhaps it's a definite integral from the interval 1 to 2. And it might have been pointed out in a Calc 1 class, but if not, I'll point it out here, that this e to the x squared function does not have a closed form antiderivative. In other words, there's no function such that e to the x squared dx is nothing like arctangent of natural log of x or something like that that we can write down without infinitely many terms. That is the antiderivative of e to the x squared. So there are several functions like that, actually. There are many, in fact, and the reason we might want to use approximate integration is because we might have come across a function of that sort. So that's sort of a classic example of a function without a closed form antiderivative. Of course, it has a derivative, that's easy, but it doesn't have an indefinite integral or an antiderivative in the sense that we've already studied in Calc 1 and now in Calc 2. So that's a primary motivation to, we can still write down what this definite integral is, and then we can still use approximation techniques to get some idea of what this value actually is. In other words, what area is underneath the curve between the value of x equals 1 and x equals 2. And that's the point of this section. So remember that with any approximation technique, we divide the interval from a to b up with n subintervals, and then we form a rectangle above each one of those n subintervals, and those rectangles are as tall as the function value. Now the question we always had about it was where do we put the function value on the top of the rectangle? So in left endpoint rules, we use the left endpoint of the subinterval, and the right endpoint, we use the right endpoint of the subinterval. For the midpoint rule, which you should have already seen in Calc 1, but we're seeing it again here in Calc 2, that's fine. We'll use the midpoint. X1 bar is the midpoint of the first interval from x0 to x1. And we'll see how to calculate that in a moment. So if we do delta x, which is the width of each of the subintervals, and that's calculated here, delta x is equal to the full length of the interval b minus a divided by the n subintervals that we desire to split our interval into. That's either given to you or we make that decision based on an amount of accuracy that we're hoping for. And we multiply that delta x, that interval length, times each of our rectangle heights. And in this case, we'll have n rectangles underneath our curve, approximating the area under the curve, just as we did in Calc 1. Of course, there are nice pictures in the textbook for this section as well. And we add delta x times each one of those function values up. Here we've just factored out delta x in the formula to make things a little bit more simple and easier to calculate. But at heart, the same thing's happening here that we did in the left and right endpoint methods, as well as midpoint approximation in Calc 1. To calculate each of the midpoints, remember that, this is our ith midpoint, first, second, third, up through the nth midpoint. We do the average of the two ends of it. So xi minus 1 plus xi. So that's the left endpoint of the subinterval plus the right endpoint, divide by 2. And that's literally the mean of the two endpoints of that subinterval. Here's that subinterval I'm talking about, of course. And remember that each of the xi's is calculated in the way that we always have. We let I run from, actually we should let I run from 0 up to n. So there's a small typo in the notes right there. So I is actually equal to 0, 1, 2, up to n. So keep that in mind. That way we start, when I is 0 in this formula right here, x0, x0 is equal to a. So we should start at a as our leftmost endpoint. And of course, when I is equal to n, the reader can check that when I is equal to n, x sub n should be equal to b. And if you follow that check, you'll see that that's the case. So that's our formula for the midpoint rule. We'll see the trapezoid rule and then Simpson's rule in a subsequent video. So let's have a look at applying this midpoint rule. So the question asks us to use the midpoint rule with n equals 4 to approximate the given integral. So let's have a look at the integral to start with. It's a definite integral from 0 to 2. We're integrating the function 1 over 1 plus x cubed with respect to x. We can see on quick glance that 1 over 1 plus x cubed, we don't have an immediate antiderivative for that. The next thought would be, is there a u substitution we can use? And what we'd most likely choose is 1 plus x cubed to be u, but there's no x squared term anywhere multiplied by this. There's just a 1. So it doesn't look like a u substitution would bring us out of this. I don't think we could find much for integration by parts either, because that usually involves a product. And this being a cubed, does it lend itself to trig substitution? So really, this is an integral that if it does have an antiderivative, it's possibly very hard to find. So if we're only looking for the area underneath this curve from 0 to 2, if we're just interested in the definite integral, we can resort to an approximation technique. In this case, we're just doing n equals 4, but we could crank n up for more resolution, skinnier rectangles, and more of them to get a more accurate approximation of the area underneath that curve. Remember, that comes at the cost of calculating that many more rectangles. At some point, it's worth it to have a computer do this work for you. Okay, so n is equal to 4. We make a note of that. The first thing we'll want to know is our rectangle width, delta x, and that's b2 minus a is 0 over n, the formula that we saw on the previous page, b minus a over n, and we have 2 minus 0 over 4, and we have 1/2 ultimately there. So each of our rectangles has a width of 1/2, or our subintervals have a length of 1/2. So our endpoints, we need to build up all of our endpoints in these intervals. We're going to go from x0 to x4. x0 should start at a, x4 is xn, so it should end at b. So in other words, x0 should be 0 and x4 should be 2. That's a nice check to have for these problems when we set up all the endpoints of our subintervals. And when we apply the formula that we have, remember this is a, which is 0, plus I equals 0, times delta x. And we iterate that formula over and over. We see that, of course, in this case, we have a 0 as the result. And then when I equals 1, we have a plus 1 times delta x. Writing the formula down more explicitly this time just to see it. We have 0 as a plus 1 times delta x. 1 times 1/2 is 1/2. 0 and 1/2 is 1/2. Of course, we could apply the formula over and over, but what we realize at this point is that each of our subintervals is an equal length of 1/2. So we just add 1/2 to each of these terms until we get to b. And that should coincide with our nth term, in this case, our 4th term. And it does, so things look like they check out. Okay, so you can either apply the formula for each of these, or you can, once you find your step size, write it out that way. Okay, but these xi values are only the endpoints of the intervals. They're not the midpoints. So we have to use them to calculate the midpoints of each of their subintervals. So x1 bar is the midpoint of the first interval. The first interval goes from x0 to x1. So we add x0 and x1, divide by 2, or use the formula from the previous page for the midpoint. And we end up with 0 plus 1/2, all times 1/2, and we get 1/4. Okay, and doing something similar, the second interval is x1 plus x2, divide by 2. Essentially, we're finding the mean of all of our endpoints, right? And this one comes out to 1/2 times 1/2 plus 1. Substituting all these values in from this list above here, or up here. And we've got 3/4 as the result for x2. And then we realize, possibly, and this is a nice catch, these are also going to step, our midpoints are also 1/2 apart. So we could use a shortcut from here forward, or continue to use the formula, either way. But I'll just say we could add 1/2 to 3/4 and get 5/4. Remember, 1/2 is 2 over 4. And then 2 over 4 plus 5/4 leads us to 7/4, and so on. We realize that 7/4 should be the midpoint of this interval. We could check that if we wanted to, but it is. And we've got all of our midpoints set up. So we're finally ready to apply the main formula. And that's the midpoint rule with n equals 4 as the approximate area underneath this curve between 0 and 2. Again, reading back from this integral at the top, remembering what it is we're approximating. And that's equal to 1/2, that's our delta x, that's times all of our function values. So again, that's our width for each of the rectangles, times each of the rectangle heights for all 4 rectangles that we're approximating underneath this curve. So f of 1/4, f of 3/4, we're just moving down our midpoints, and our function is 1 over 1 plus x cubed. So there's 1 over 1 plus 1/4 cubed, and so on for 3/4, 5/4, and 7/4. And it looks like we can simplify this a bit by multiplying both denominator and numerator by 64 in each one of these fractions. And doing so cancels this 1/64th, and these denominators is 64. Only what we'll have is each of these numbers, the numerators here, plus 64. And that's essentially what's happened for all of these values in the denominator. And of course, it's easy to see what's happened in the numerator because that was just 64 times each of those ones. So the arithmetic details are left off. Students can handle that. This is simplified a little further to factor out this common factor of 64. Again, at this point, or even this point, you can just start plugging things into a calculator or an online calculator, computer, something like that, and start finding out what things are as decimals. This has been done mostly by hand, and it actually cuts off here because there's not much more work to do by hand. Notice in this step, we factored 64 out. It was divided by that 2, thanks to the 1/2 multiple in front of the brackets. We end up with 32 times these more simplified fractions. So a little bit of simplification by hand might save what you have to enter into a computer, but or a calculator. But at the end of the day, either way is just fine. On a written test, something like this could be okay, unless a calculator is handy or allowed, or if you're asked to express it as a decimal. Okay, so that's one iteration of the midpoint rule. So let's meet the trapezoid rule and try it. None of these things are very different from one function to the next. It's just a matter of applying the formula. So the trapezoid rule, denoted t sub n, for a similar integral from a to b f of x dx. The trapezoid rule is delta x divided by 2, so there's a little bit of a difference in our formula, and that's times each of our, we kind of think about this as a rectangle height, but now they're actually trapezoid heights. You can think of them in that sense. The formula has been built to form these as trapezoids. But what we have in this case is this is just f of x naught. That's just the subinterval endpoint. Same with x1, x2, and all the way up to xn. So remember that x naught will be a and xn will be b. So there's a and b evaluated on the left and on the right. And notice that they're the only ones with a coefficient of 1 inside this bracket. Everything else that's added has a coefficient of 2. Now, if we did the geometry to work this out, we'd see that this is, in fact, how this does form trapezoids at the top of each of our rectangles. But there's a nice image in the textbook and a little explanation that explains that to us. For now, let's just see this formula in action. So use the trapezoid rule with n equals 4 to approximate the given integral. And again, we've got the same function. We see that there's probably not an easy antiderivative available. So we'll, it makes sense to consider integrating this approximately. So delta x, it's b minus a over n. 2 minus 0 over 4, we get 1/2 once again. And x naught then, we use our formula for xi. It's a plus 0 times delta x. A is 0. And then 0 times delta x is 0, so x naught again is 0. Also, we remember that x naught should be a, which is 0. Now, we realize we're stepping by 1/2. This is an easy fraction to add. So we just add 1/2 to x naught to get x1. We add 1/2 to that to get x2. We keep stepping to the right by adding 1/2 till we arrive at 2. We check to make sure that x4 and n equals 4, we should be at b at this point. And in fact, we are. That's a nice check. And below, we're ready to implement the trapezoid formula. It's a little bit quicker and a little bit easier than the midpoint formula because it just involves these endpoints directly and it doesn't actually involve a midpoint. So t sub 4 is this delta x over 2. So our delta x is 1/2. That's divided by 2. That's the formula giving us that denominator of 2. And we have 1 plus 1 over 0 cubed. We have 1 plus 1 over 2, 2. So from our formula, we have a 2 from the formula in the beige box times f of 1. And f of 1 is 1 over 1 plus 1/2 cubed. That's 1/2 cubed is 1/8. Similarly, 2 comes from the formula, and that's over 1 plus 1 cubed. And there's 1 cubed. It's just 1. And then similarly, we work down the line. 3/2 cubed is 27 over 8. Coefficient of 2, thanks to the formula. We're at the very end, so we switch back to just a coefficient of 1 times f of x sub n, or f of 2, and 2 cubed is 8. So there we have that fraction. Again, doing some similar fraction simplifications, we arrive at maybe a line like this, being careful with the factor out front. Also, 1/2 divided by 2 is 1/4, or 1/2 times 1/2. And ultimately this, I settled on this for whatever reason, just because I was doing things by hand and it didn't look like it get much simpler. Probably a nice time to start plugging things into a calculator would be right about here. You won't make as many mistakes with these compound fractions, but you could of course use this line if you want to. So that's just a matter of taste, how to simplify. Web assignment will be very clear. The homework and quizzes will be very clear about how to express your answer, and so will any tests. Or worksheets might be a little bit less clear, in which case you have the liberty to leave answers like this potentially. So what good is an approximation if we don't have some idea of how much error is involved in the approximation? So these are the error bounds that we'll see for the trapezoid rule and the midpoint rule. One in the next. So what is easy about this is if we're looking at an integral from a to b of some function f of x dx, b minus a, that's very easy to find. Those are the limits of integration. N, that's easy to find. That's the number of rectangles we're going to use. But k is the tricky thing in all of these cases. In the case of the midpoint and trapezoid rules, we see that k, per the formula, is the absolute bound of the second derivative of the function. In other words, the upper bound for the absolute value of the second derivative. So we'll see that that's actually the tedious part of these. That's where all the work is, to come up with these error bounds. But it is a very useful thing to be able to calculate and know that the amount of error in your trapezoid approximation is less than or equal to some number. Then you could say, at worst, my approximation is this far off. We have that much error in it. And notice, if you felt that your approximation was just, you calculated this and you realize you don't like the look of that, you don't want that much error, well, you can't change b and a, and you can't change k because you don't want to change your function, since that's what you're integrating. You can change n, and you can make n significantly larger. And if you make that denominator larger, you're going to make the whole number overall here, the whole fraction, smaller. So that will shrink the error bound of the trapezoid rule, and that'll give you a more accurate approximation. And notice all of that looks the same for the midpoint rule. The only difference is this factor of 24 in the denominator of the midpoint rule's error. So it looks like between the trapezoid rule and the midpoint rule, the only differences are those constants. And so I'd ask, which one is more accurate, the midpoint rule or the trapezoid rule, if we're going to use the same number of rectangles, the same n? Try to answer that to yourself. Pause it for a minute, think about it if you need to. Okay, if you're back, well then of course the 24 in the denominator makes this overall fraction smaller than what the 12 does to this, right? This is half as much as this overall for each of these numbers, since 24 is twice as much as 12. If the denominator of the lower fraction is 2 times larger than the upper fraction, than the first one, then of course this is going to be half the error. So it's half the size overall. So it looks like the midpoint rule is more accurate if we're using the same number of ends, the same number of subrectangles. Okay, so let's get to work. Let's use this. They ask us to use the error bound formulas to determine a bound on the error for each of the approximations T10 and M10. So a trapezoid rule with n equals 10 and a midpoint rule with n equals 10. So note that n is 10 in both these cases. We start to set up our error bound for the trapezoid rule with n equals 10. So we use the formula up above in the box, write that down. We know that the error of our trapezoid approximation with n equals 10 is going to be k times 2 minus 1 cubed. It's part of the formula. And 2 minus 1 is b minus a from the integral there. And then that's all divided by 12, again from the formula, times n squared. N equals 10, so that's 10 squared. Now, the one thing we can't fill in right away is k. K takes some work. Remember, k is the bound of the absolute value of the second derivative. So we need to go looking for k to determine this. So we need to find the second derivative of this function and see whether or not we can establish a bound on it. Preferably, a least upper bound would be preferred for the absolute value of the second derivative. So to find k, which is greater than or equal to f double prime of x, or an upper bound for f double prime of x, absolute value of that, we just differentiate. So f of x is this function. So first derivative, it's e to the x to the negative 1 times the derivative, remember the chain rule, of x to the negative 1. That term is the derivative of x to the negative 1. So chain rule gives us this, and we have negative x to the negative 2 times e to the x to the negative 1. It's get a little complicated because the second derivative, we're going to have a product rule as well as our chain rules now. So our first derivative, taking the derivative with respect to the first term, negative x to the negative 2, we should arrive at 2x to the negative 3. I'll let the reader check those details. Times e times x to the negative 1, e to the x to the negative 1, which is the first term of our product rule, differentiating this product. Derivative first times second. Now it's the second function, it's plus the first times the derivative of the second. We've already calculated the derivative of e to the x to the negative 1, so we recycle that information down here. Pretty easy to do. We just have to simplify these powers of x. So we have 2x to the negative 3, e to the x to the negative 1. There are multiple things we could do here. If we have a graphing utility available, we might have a look and see whether or not this function is increasing or decreasing on this interval. If it happens to be increasing on the interval, then we'll know that its maximum is on the right-hand side. That's if it's positive, of course. If it's decreasing, then its maximum will be on the left-hand side if the function's positive for all these values. Now let's double check. If we look at our interval from 1 to 2, this function is always positive. So that's good news. Now it's just a matter of knowing whether or not it's increasing or decreasing. Remember, we can check using the derivative of this function even. So we take the derivative of all of this, f triple prime of x, and determine whether or not it's positive or negative on the interval from 1 to 2. And that's what this is telling us to do. Possibly we could do the full closed interval test, and that's to look for any local minima or maximum. In other words, take another derivative here, set that equal to 0, and see what we can find from here. But it looks like what I ultimately settled on was just having a look at the graph. We have tools to graph these things, so let's look. By the graph, I declared that the max occurs at x equals 1. Well, this is our interval 1 to 2, so it must have meant, and if the reader graphs this function, which I highly encourage you to do, you'll see that the function is decreasing on the interval from 1 to 2. It's positive and it's decreasing, so its maximum value occurs on the left. In other words, it's furthest from the y-axis when x is equal to 1. So if that's the case, then its maximum value, so the maximum value of f double prime of x occurs at 1. So that max value is f double prime of 1. We plug 1 in for x. We have this expression here, and that simplifies to 3 times e. So we choose or set k to be the absolute value of 3e. And really, we might have written all this as absolute value too as we work through, but we can wait till we're at the end of it once we know where the max occurs or the min if things were negative. And we set k equal to absolute value of 3e, which is just 3e. And now we know what choice of e to use in this. So on the next page, we wrap it up and we see that for our trapezoid rule with n equals 10, our error bound on that trapezoid rule is less than or equal to 3e, there's our k, times 2 minus 1 cubed over 12 times 10 squared. And we end up with, well, we simplify things and have e over 400. Now, of course, on a test without a calculator or some kind of resource to calculate this directly, that's just fine. Worksheet, that should be fine as well. But WebAssign, anywhere we have a calculator available, I'm sure you'll have clear instructions on how that answer needs to be expressed as a decimal or to how many places or as a simplified fraction like this one, so on. Now I've left E sub m to the reader as an exercise, and I'll let the reader compare what they come out to, try to get an expression that looks like this, and see if the error is in fact half of this one. So I guess the hint is the error bound for the midpoint rule should be E over 800. See if you can arrive at that calculation. So that's it for the first half of 6.5. The next video will cover Simpson's rule for error bound for approximating and the error bounds on Simpson's rule, and that'll be it for 6.5.